This video is part 1 for time series forecasting with the profit model. We will present step-by-step coding in the next video. For the current video, we will focus on the advantages and features of the profit model. A lot of packages look like this diagram. You take some raw data and align it to a specific input format for the package. Profit expects to see a sequence of measurements over time with a timestamp. It is pretty easy. The tool is an abstraction layer on top of that standardized data that wraps it and provides functionality, so it can provide an explanation, it can provide predictions, and it can provide diagnostics about how well it fit or why it fit the way that it did. It addresses the question of how to get a tool into people's hands and not require them to be time series experts. It's a fairly simple method, so when it fails in predictable ways. It's easy for people to understand what it is doing and why it is doing it. We use time series forecasting in lots of business contexts, projecting sales for goal setting, capacity planning, etc. Some forecasting techniques require measurements recorded over successive, equally spaced intervals of time. But as we will see, this is not required for the profit model. On the right-hand side, we see two time series for Stack Overflow mentions of machine learning and the other for time series. As we can see, machine learning has grown dramatically while time series has more modest growth. Most data scientists have little exposure to time series analysis. ARIMA models assume that the relationships between past and future observations in the time series remain constant over time. Stationarity ensures that these relationships do not change, allowing the model to make reliable predictions based on historical patterns. Stationarity simplifies the modeling process by stabilizing the statistical properties of the time series. For example, a constant mean and variance make it easier to estimate model parameters and interpret the results. In ARIMA, differencing is often used to achieve stationarity if the original time series is non-stationary. Differencing removes trends and other systematic patterns, making the data stationary and suitable for modeling with ARIMA. The I in ARIMA stands for integrated, or order of integration, which is the minimum number of differences required to obtain stationarity. Autocorrelation, which we see on the right-hand side, shows a regression line running perfectly through the data, but our linear trend line ignores the correlation of the data over time. Here, each of the values is closely related to the previous value. The AR component accounts for the dependence of the current value on previous values in the time series. This helps capture trends and patterns that persist over time. The MA, or moving average component, filters out short-term fluctuations or noise in the data, providing a smooth representation of the time series. When we combine the two, the AR component accounts for long-term dependencies and trends, while the MA component addresses short-term fluctuations and irregularities, and as I mentioned before, the I stands for integration. One big difference between profit and ARIMA is that profit does not explicitly evolve in time like ARIMA. It is actually a regression model. So, we treat the forecast problem as a regression problem. When you look through course catalogs for data science programs, there might be one class on forecasting, and it may not even be a requirement. Additionally, there are lots of nuances to fitting ARIMA models, and the chances of gaining command over these in a short amount of time is very low. But every data scientist knows linear regression very well. What is Facebook profit? There are 5 things I would like to point out. Number 1. Profit was developed by Facebook's core data science team in 2017. Number 2. Profit uses STAN, which is the Stanford AI, Natural Language Processing. It's a probabilistic programming language and inference engine. The Bayesian framework in Profit helps us make predictions in a more flexible and informed way, taking into account both what we already know and what we learn from new data. It gives us not just one answer, but a range of possibilities, along with a measure of how certain we can be in those answers. In the context of the Facebook profit model, STAN is utilized for the underlying Bayesian inference process. It fits the profit model to the historical time series data, sampling from the posterior distribution of model parameters. This process involves exploring the parameter space to find the most likely values given the observed data and prior information. It does this behind the scenes and can be used by non-statisticians. Number 3. Holidays are simply dummy-coded, and we can add to this a lower and upper window. For example, we might want to add a lower window of 6 days before Black Friday and 2 days after Black Friday as part of our single coding of the Black Friday event. Number 4. Profit is easily customizable, as we will see in the coding portion of the Part 2 video. And finally, number 5. There is built-in cross-validation. In all analysis, there are only two things. There is signal and there is noise. Our job as analysts is to extract the signal from the noise. This signal can be decomposed into a couple of dimensions. As previously mentioned, the stand package uses piecewise regression to extract the trend. For the seasonality, the stand package uses Fourier series to pull out the seasonal cycle. For holidays, these will be identified by dummy codes in your input data and specified in your profit code. And finally, your external inputs are based on your domain expertise. These external regressors, or inputs, are used to help extract the signal from the noise. For example, if you have a time series of your company's sales, you might use the changes in your marketing spending over time as an input. As you increase your marketing spending, you should see an increase in your sales and therefore help explain the variability in your sales. Imagine you have a scatter plot of data points that don't follow a single straight line trend. Instead of trying to fit one line to all the points, piecewise regression breaks the data into segments and fits a separate line to each segment. Piecewise regression looks for points in the data where the relationship between the variables changes. These are called breakpoints, or knots. It's like finding where the slope of the scatter plot suddenly changes. Once the breakpoints are identified, piecewise regression fits a straight line to each segment of the data between the breakpoints. Each line captures the trend or relationship within that specific range of the data. Piecewise regression is useful when the relationship between the variables is not linear throughout the entire range of the data. It allows us to capture more complex patterns and variations in the data that wouldn't be adequately represented by a single straight line. Let us visualize you're trying to understand the repeating patterns in a time series dataset, such as the sales of ice cream throughout the year. Fourier components help us break down these patterns into simpler, more understandable pieces, like building blocks. Think of it like music. When you hear a complex sound, like a song, it's actually made up of different notes played together. Similarly, in time series data, the complex pattern we see is made up of simpler repeating patterns. Fourier components help us identify and describe these repeating patterns. They are like musical notes that, when combined in the right way, can recreate the original melody. These represent different frequencies or cycles in the data. For example, one component might capture the yearly seasonality, while another might capture monthly or weekly patterns. Each component represents a building block of the overall pattern. By combining these components in the right proportions, we can recreate the original pattern of the data. These components allow us to capture complex seasonal patterns, even if they're not perfectly regular. For example, if the seasonal pattern is not exactly 1 year long, Fourier components can still capture it by including multiple frequencies. Fourier components help us understand and describe the seasonal patterns in time series data by breaking them down into simpler, more understandable pieces. They allow us to capture complex seasonal patterns and make better predictions based on the underlying structure of the data. The out-of-the-box output presents insightful charts that are easily understood by non-experts. The impact for holidays and events are straightforward. The weekly trends are intuitive and will correspond to domain knowledge. And finally, the seasonal cycle is automatically detected and captured in detail, providing a clear depiction of month-over-month changes. Additionally, since the profit model is a variation on a regression model, missing data from the time series is easily accommodated. As we will see in the second part of this video series, the profit model is easy to code, scalable, and fast at computation. As always, I value your time and I appreciate any comments to help guide future videos.